I think we're closer to now 1,000 servers. We run out of multiple data centers. Lots of visits. 300 million a week. That's around the same as eBay, Walmart, and all of these other platforms. So it's really up there. Here's a really big pretentious picture of me, but I don't think we need to talk more to that. So one of the big motivations for talking about how to build more reliable systems is that we're all building more and more distributed systems. A lot of people talk about microservices now. I'll rant about that later and why I don't think that's a particularly good idea in every context. Regardless, we live in a world now where a lot of things are outside of our control. We don't run our data centers anymore the same way that we used to do 5-10 years ago. They've sort of gone the same way as the power plant, where now we give this off to Amazon and other places. This means that we now have network infrastructure and stuff like that that will fail and can cause our application to fail when we don't have any visibility into it. So there are all these different components, like cables can get cut. This sometimes happens. We get a call from our RSP saying, sorry guys, we won't have connectivity until tomorrow because someone, cut over a line. The routers fail, all this stuff fails. Even if you're running in your own data center, you have the full visibility, you just have to accept that all of these things will fail. In the talk that I did in RUCO 2 weeks ago, I talked about how cosmic arrays are actually a thing and how it can cause some kind of really interesting security concerns and stuff like that. If we have time, I'll talk a bit about that later. It's really interesting stuff. It actually happens about 2 times per hour, which is much more than you might think. So, why I think this is so important is because, especially in the Ruby community, this is not something we talk about a lot. A lot of the knowledge that we have from here is stuff that I've compiled from ancient Java books, talking to people from the Java world and so on. It's a lot more mature in this area. But for us at Shopify, this was the biggest win we did in 2014, and we did it way, way too late. So I want to talk a lot about what we did and sort of help you, some of the mental models that we developed internally that are really helpful ways of thinking about this stuff. We are now much more confident in what happens when different parts of our systems fail, and this is really a peace of mind. I get woken up very, very rarely now, even though I'm on call a lot. And just the fact that you know what happens when different components fail, and you sort of get the peace of mind of knowing, okay, when this server fails, I know that the customer impact is this, and so on and so on. And what sort of made it happen is that this time of year is really, really, really critical for us. The American Thanksgiving is in a couple weeks. And what happens then is that you have all these American families, and they get tired of their families, and then they go to the mall and they buy, and then the malls found that out, and then they give them discounts, and then people do this. And this is really terrifying for us because that sort of culture also developed online, and which means that Black Friday and Cyber Monday, which is the Monday after the Thanksgiving Friday, is all eyes are upon us. We do crazy amounts of GMV, and I think last year we were approaching Amazon, and I think this year we might expect to exceed it across all of our shops. So it's a lot of volume. Especially this year is really critical because we went public in the spring. So this is the first Black Friday, Cyber Monday where we're on as a public company. We joke a lot about the stock ticker and having sort of automatic rollbacks if the stock ticker goes down. But this might be the day where we have a Datadog dashboard of the stock ticker, just for kicks. We're fairly confident this year, but last year we weren't. What happened was that around the time when I was here last year and ranting about Docker in August, when I was in the airport on my way home, what happened was that one of our Redis servers failed. And I'm not going to go into the depth of how this failed because it was actually the network infrastructure's fault, but it took us 45 minutes to recover from this. Then the same thing or something similar to that happened about a week later. And people were like, why the fuck is the entire thing down when once the Redis server fails, even if the failover fails? And so there's a lot of really embarrassing things that happened, and we got really, really worried for Black Friday and Cyber Monday. We started really focusing on how can our application respond better when all these different components fail. And they will fail. So what I want to talk about is this term called resiliency, and what it sort of boils down to, and if you take one thing away from this presentation, it should be that when you're building all these systems, you're building overall reliable systems from all these unreliable components that you don't have any control over. Routers, cables, network cables, some like PayPal, FedEx, all this shit that can fail. You have zero control over it. So what you want to do is you want to loosely couple all of this. Otherwise, you're going to suffer the fate of this equation. I call it a microservice equation because I like to throw this in the head of people who say that microservices is where everything is at. And what you need to realize is that if you have tons of services and they all talk to each other, and you don't think about what happens when these services fail, then you have this like tightly coupled, you can think of it as like a 2D matrix where everything talks to each other. And if one of these things fail, if one of these fields in this matrix fails, then your entire application falls over. And if you don't have any overview into this, then you have to assume the worst case is this, which is the availability of every single servers you have in your system. If one of them fails, well, then the entire thing fails. Well, in that case, your uptime is now this. You might have 4 nines on each component, which is very reasonable, and then you take that to the power of how many services you have, and then you have your uptime. Now, this looks something like this if you graph it, and if you know anything about exponentials, they're not fun when they work against you. And if you have something like 4 nines on all of your components, very, very quickly, as you go to 100 services, and which is not unreasonable in an app when you think about all the external APIs and all the things that can fail, it really goes down to maybe 98%, which is about a week, if not more, of downtime a year. So this is really important to realize, because it means that you need to think about how you tightly couple everything so that when something fails over here, the thing over here responds in a good manner. Because really you're only as good as your weakest single point of failure here. And it also, another realization to come out of that is that it means that if you're adding components, you're actually decreasing availability unless you can prove that adding that component, when that fails, that it doesn't compromise the performance or the availability of the entire system. And now, if you have microservices, this looks even worse. But we can't really kid ourselves. Shopify is pretty much a monolithic application, just like GoMore. And we have tens of dependencies anyway. We have relational databases, tons of shards that all have many, many servers, Redis servers, Memcached servers, Elasticsearch servers. We talk to all these shipping APIs, payment gateways, all this stuff that can fail and we have zero control over it. So this is really relevant for everyone. And I think that the most important thing is this thing I sort of touched on before, which is to loosely couple everything. And we call this fallbacks internally, where we can sort of define that as your application has some kind of primary functionality when it talks to something. It might be talking to some storage that handles sessions, or some service that handles shipping rates. And if that service works, well, then you have your primary responsibility of, well, signing people in or showing them right shipping rates. But then you can have some kind of fallback behavior, some secondary behavior that is reasonable in that case. In the case of a shipping provider failing, you can just not allow people to ship with that, and then just sort of gray it out. And then if USPS fails, you just gray it out and show them FedEx, which is a reasonable secondary behavior. Or if it's something like sessions, which we'll get into in a second. I'll show that in just a second. So if we have a Shopify store here, this is a store that can drive about 500,000 visitors per minute when they have big sales. They sell shoes in New York, very, very large. And when you look at this, it's actually made of a lot of different components. You might have something like when you're going to and browse the store and search it, that might come from a search service or a search backend like Elasticsearch. You have your cart stored somewhere. It might be in a relational database, a Redis and Memcached, something like that. Sessions, which is also stored in some kind of database. You have your CDN where images come from, MySQL shard, and in reality there are even more things here. And this is one of the simpler pages. So it's talking to all these different things, and if one of these areas fail, well, we need some kind of better behavior than just showing a 500, right? Because in something like Ruby and other high-level languages, the default behavior is just that it raises an exception. And this sort of breaks this principle that we were talking about before, where you have a single dependency compromising the availability of the entire platform in this case. In this case, we can play with the session storage failing. And a much better way of handling that is just rescue that exception and sign the person out. They can still browse the store, they can still purchase things, and we even have jobs that retry and backfill and associate emails with customer accounts. So this sort of thing just works, and it's super transparent. And that was really, really easy to do. It took someone a couple of hours to do. And now we have a much better behavior, and when our session storage fails, it's really not a problem. This also made something like data center failovers way easier, because maybe we just fail over to an empty instance and nobody gave a shit. So it's really, really simple. And you can do all kinds of crazy sophisticated things, like if your cart storage fails, you can just add it to local storage with something like JavaScript and persist it to backend when it's back up. And you do arbitrarily complex things. We don't do anything crazy right now, because there's also sort of the fundamental balance between having your application be resilient to something and then actually having the backend not fail as much. This is a balance we'll talk a little bit about later. But the fact of the matter here is that I'm super happy, because I know that when this fails, it's fine. The customers probably won't even notice. They'll probably go ahead and buy their thing without even noticing that their customer account is not there. And the merchant, the same thing. This has zero effect on GMV, which is how much money we process. So it could look something like this, right? You have your controller here, and you have some kind of a user you set, probably in a filter. and you find the user from the session. And this is not resilient code if that session, which could be going to a memcache, it could be going to a Redis or something like that. If you're in a cookie, you're fine, but a lot of people aren't. So this is a hard dependency, but if you then rescue that exception and just return some kind of default value like a nil, then your template probably already handles that, right? You have something like if current user, do this, and then if there's no user, well, you're already good. So it's only just two lines of code. There's a lot of people who've talked a lot about this in the past in the Ruby community as sort of the null pattern, and there are more sophisticated ways of handling this, because if you have this sprinkled all over your code, that makes things really complex. So you just return empty data structures everywhere. Another example of this would be if you might be caching your tags for products in some kind of data store for whatever reason. But again, if the Redis data store is down, even though all the other information might come from other places, then this is not resilient either. Now you have this little orthogonal piece called products tags that just took down everything, which doesn't make sense, right? If you have a status or an incident report that says that all of Shopify was down because the storage engine that stores the product tags was down, well, the CEO is going to scream at you. So what you have again, you just return back an empty data structure, maybe log something to an error report or something like that. You probably don't even need to, because you should have monitoring on that infrastructure by itself, and just be confident in your application working well. We actually have a lot of Ruby, or in this case, Ruby metaprogramming around all this stuff to make sure that you can't call different data stores that are sort of orthogonal to Shopify without having fallback specified. I'm not going to go into depth with how that's, but everyone who's done their fair share of Ruby will know that that's possible. The problem though is that now you have these sort of sprinkled all over, and you can sort of think about this as having like a decorator. We don't really allow people to just access Redis or Memcache just like that, where you need to create some kind of abstraction that people can reuse. In this case, something like a persistent set, and so on. And in this case, it's sort of abstracted away for developers, and you're only responsible for thinking about resiliency if you're implementing new data structures and so on. So you don't have to think about, most of our developers don't have to think about resiliency at all. And even if they don't think about it and they're completely new, some tests will fail saying, hey, you didn't specify a fallback, and then link you to some documentation about how to deal with resiliency in Shopify. So it's really very automatic, and the process is we were just talking about before, being very independent from each other. And in this case, because a test fails on CI and provides you the right documentation, this is a pattern we use a lot in Shopify when we have hundreds of people working on the same app. And this is kind of hard to get an overview of, because now you have all these different things and you want it to fail in nice ways. So you sort of need a mental model or some kind of model for thinking about all these dependencies. So when we started doing this, we created this sort of matrix where on the top here you have the different sections of your application that are sort of business critical. In our case, that's something like, can people check out? There could be another one with the API, the administration, like managing products and so on. Storefront, is that up? And sort of you can have an ordered priority here as well. Our number one priority is that storefront is up, number two is that checkout is up, number three is that admin is up, because that's sort of what impacts our business the most. Sometimes checkout will be down, but the storefront will be up. I don't think we've had storefront be down for more than a year because of all these primitives, but checkout is much more complicated, has more moving pieces. So what you have then is you have these cells, and each cell says, okay, if this service on the left or dependency on the left is unavailable, what happens to the section? And red here, or unavailable for the colorblind, means that you, the section on the top is completely unavailable when the service on the left is down. Degraded can be something else where you handle the functionality in this graceful way. You might show the user that something is going wrong. Again, it's really, really important to keep the user in the loop. If they can't sign in, there's a big difference between showing a user that they entered the wrong password or saying, hey, sorry, you can't sign in for the next couple of minutes. So that's sort of the degraded one. Available is that no one really cares. It's completely fine. And sort of your mission here should be to get all the cells to be either yellow or green. And this is a really, really powerful way of thinking about it. So what's really great about sort of the Ruby community and very endemic to all the Rubyists is that the first thing they will think about when they see this is, okay, so how do I test this? Turns out that's really hard, and you can do something like have a mock, but as we all know with mocks of external dependencies, often it ends up masking just as many things that it uncovers. So it doesn't really work well. It means that you have to mock every single adapter, like how the Memcache client reacts is very different from the Redis client, MySQL client, or Elasticsearch client. You have to do that for all of them. It's also sort of at the wrong level because now you're not checking that the driver is actually handling these failures in the right way. So what we wanted to do was do the emulation of failures for our test suite at the TCP level. And there exists a lot of proxies out there that emulate failures. The problem is that none of them are scriptable. What I wanted to be able to do was something like this. I just have a block, and then I say within this block, this service is slow. Or within this block, I can't access Redis and stuff like that. And now I can write tests for all this stuff, right? I can take Redis down and then see that, write an integration test, seeing that when I hit this endpoint and Redis is down, everything is fine. Or when the MySQL master is down, we can still query the shop because the shop might be cached in Memcache, things like that. So now we can write tests for every single one of these columns. And the way that this works is just a TCP proxy. You query it with HTTP requests saying like, hey, now this is down, now it's up again, and then you just have Ruby closures around all this stuff, and it works really, really, really well. And we even have a tool here in the development environment where we have this thing called TurboBar, which has a lot of, which is developed by my team, the performance team, where we help people sort of analyze how to make page loads faster. Now it also has a place where you can go and say, hey, the MySQL shard 1 is slow or it's down and stuff like that. And this took us like an afternoon to create with one of the front end devs because the API is so simple to use. And now we can write these tests, right? Test storefront resilient to session storage. So we say toxic proxy Redis sessions is down, get the front page and make sure that everything is fine. And now we can take this entire matrix again and we can write tests for every single one of these cells, right? So test section A is up when the message queue some message queue is down, right? Test that section B is up when data B, or in this case that it fails, because you also want the reds, sort of the unavailable fields to be tested so that you have a great overview of everything that's happening. And you can do really, really advanced things in your fallbacks and your integration tests. We don't really do that. So what happens then is that you figure out that also Rails has a shit ton of bugs because they've never tested for this either. Fortunately for all of you, if you're on Rails 4.2 and 5.0, most of these are gone. There's still this one in here which the Ruby or the Rails core people on at Shopify are now working on fixing. And if you're really clever, you can already spot the bug, but it took me a really long time staring at this. So the problem is this, right? So there's this query cache middleware, which is a middleware very early on in the middleware stack, where it establishes on the connection, it establishes a query cache object. And between every request, it resets that query cache, right? And the query cache is that if you do like select star from shops, then the next time you do it, it just caches it in memory in some kind of hash, really simple. So what this middleware does is it's just responsible for sort of initializing that cache and make sure it's not to enable it if it's disabled and so on, and then reset the cache after the request so you're not reusing things between requests and things like that. But the problem here is that this is the reason why if you have a MySQL database or some kind of relational database as your primary in your Rails app, and that is down, and you hit an action that doesn't touch the database at all, your app is that you can't access it. It's down. This is a bug in Rails right now in every single Rails app because of this middleware. Where when you call the middleware, it has this line here where it calls active record based on connection, and if active record doesn't have a connection, it will try to establish one. So in this case, it can't, so it won't skip it, and there's no rescue around it. So we just have a monkey patch that rescues that, and then just calls and skips the query cache middleware and sees it if it can get through anyway. But this means that even if you have something like Memcache in front of everything, by default in Rails, it's still going to fail when your relational database is down. And there's tons of other bugs like this in Rails, like one where if you had 5 requests in a row fail, then on the 6th request it would just start failing because of active record pool management. Yeah, the worst thing that ever happened to Rails was that they tried to make it multi-threaded. That was really silly. Okay, so now we have these fallbacks everywhere, and we have this resiliency matrix, and it's now all yellow and green and dandy. And now we realized on the team that, okay, most of the time systems don't really fail where we just get an exception right away. That's really great when it does, but that's really, really, really rare. What happens most of the time is that something gets slow, or it's slow some of the time, or someone forgot to add an index and they deploy and everything is slow, and some network partition happens where some servers can talk to each other, and for others it's slow, or some router is failing, or the network is congested, or all these kinds of crazy things happen. And this is really where the majority of the failures are, and where we spent probably 4 to 5 months trying to figure out how to deal with slowness. I don't know if you've ever seen a graph like this where your response time increases. I think this particular example is because someone deployed an ignore index, and the ignore index was different between how a read slave reacted to it and our master for that shard. So what happened then was that the response time climbed up because it was doing a full table scan. And as a result of that, because we're capacity planned to maybe 100 millisecond response time, we just couldn't handle as much throughput.
Simon, why did you blur the y-axis?
Well, it's because we're a public company now, and I can't actually say how much throughput we have.
Okay, I was just
think
curious.
In this particular example, it's like, I think I can say it now because now our CEO tweeted it how much our throughput is. So it's around like 400, 500K daily. And then it goes down to around 200K or so. So it's sort of intuitive that if your response time goes up and you have all these things working off work, then they can't do as much work because they're waiting. I'll illustrate this in a second. And to that you might say, well, okay, we'll just add timeouts to everything. But if you then go back and say, hey, if I had a 20-second timeout to everything, well, that's why this thing is capped here, because we had a MySQL timeout of 20 seconds, right? Now every request takes 20 seconds. So timeouts are not really enough. So what do you do then? And even then, most things have terrible timeouts. Like Unicorn has a default 60-second timeout. NetHTTP, I don't think it's even 60 seconds. Like it's probably the TCP timeout, which is shock high. MySQL, Redis, AWS Gem, Memcache Gem, so on and so on. And you sort of pick some other timeouts, and you also need to have a timeout high enough to account for outliers, because you might have some customers that have a lot of orders and it takes longer for them, and that's actually fine most of the time, but you don't want sort of your average to be there. And you can do crazy heuristics around, well, okay, if it's this section of the admin, then it's fine, or you can have like a Ruby block. Like GitHub has this horrendous API where they say, oh, this is a slow query, so it's fine if it takes longer, but your worst case is still the same. If that query becomes slow, you're fucked. So this is what happened. To try and illustrate why that's problematic, we can say here we have a Unicorn, which is sort of the Ruby web server that we use. And now something is slow and you go to /impacted and the response time is 500 milliseconds. And the normal response time is something like 20 milliseconds, so you get a /OK. But it's backed up between that impacted one. So your response time goes up as a result. Now you might have another OK and it's still behind this impacted one. And then you get another impacted one, you have this problem, right? Where all these slow requests are backing up all the fast requests. Another example to illustrate this would be something like this. You have sort of a very classic web infrastructure where you have a load balancer. It might be doing something like 400 RPS. You have all these containers that are serving requests at around 10 millisecond response time. They're accessing all these data stores a lot. They have very, very fast response times, like 0.2 milliseconds is very typical for something like MySQL. They're accessing other services and so on. And it really doesn't have to be very much that they have to increase before your entire chain sort of falls over. So when the fastest part of your stack becomes just a little bit slower, it impacts everything. And some of these requests, like this one, actually only accesses this one, but it's still impacted by the slowness of this one. So this is a really big problem. So sort of what I'm trying to convince you of is that timeouts are not quite good enough. Your response time still suffers. Your capacity is still reduced no matter what you do. Setting timeouts is really problematic. If you put them really, really low, then sort of dropping a single packet internally won't even allow for the TCP retransmit. And even then, 10 milliseconds is also a response time increase that you don't want. And so you need ways to fail even faster. So I grabbed this book called Release It, which is probably the best book I've read in software ever. And if this is interesting to you, I definitely recommend reading it. And it just talks about this guy who's been working on like airline systems, very mission critical systems for a really long time, and how all these different patterns that they used. And it talks about some heuristics for failing faster than timeouts, which is really what you need here. If you want to save your response time, then you need to fail really fast and let your fallbacks handle sort of the consequences of these faster failures. So the two primitives that we chose to implement that complement each other really well are circuit breakers. And sort of the pattern there is that the heuristic is that if you access a resource and it fails once, then it's fairly likely to fail again. So you set some kind of threshold where you say, if I've accessed this resource, say 3 times and it's failed 3 times, then I'm just going to not cure it and fail instantly for the next 20 seconds. And then I'll try once more. And if that fails, well, then I'll close it for the next 20 seconds again. And that means that you give your failing components a little bit a moment time to breathe. If you make all these independent, it also means that you sort of don't have the thundering herd problem of tons of clients querying the resource when it's up again, which can sort of just make the thing go around and around. So this is a really, really great heuristic. The problem with that is that it takes this many failures, like 3 to 5 failures, before it gets to that point. And if your timeout is 20 seconds, that means that you are somewhat degraded for over a minute. So this is sort of the chart, but I think we're going to skip that. So circuit breakers, gives your failing component some room to breathe after these failures. Fails really fast after several timeouts. Just fail instantly. There's just a Boolean flag that says you can access it, you can't access it. And if some timeouts are high, circuit breakers don't help much. Capacity is reduced until they kick in, which is sort of the problem that I was explaining before. So we need something to complement these circuit breakers to make things fail even faster. Because the circuit breaker is great is because it forces everything to stop querying it for a set amount of time, but you need to get there even faster than you can do with timeouts. So we use another heuristic called bulkheads, where in front of every resource, before you query it, you grab a ticket. It's sort of like, you have to have a ticket to query the resource. So in this case, the resources over here become slow, you grab a ticket, you try to talk to it, and now another thing talks to this thing, and now there's 0 tickets left, and this data store is still slow. And this means that when this third container here tries to access the slow resource, it is just rejected instantaneously. And that frees up capacity now to access the still fast resource. And you can imagine this as it scales up, it gives your infrastructure sort of room to breathe. It means that you do lose some capacity of these containers that are trying to query the slow resource, but you can control how much. If you have 100 workers in total and your global ticket count is 20, it means you only lose 20% of capacity. So you have some kind of upper limit always as to how much capacity you lose when something is slow. And you're not doing any crazy heuristics. Your only heuristic here is that when this many resources are trying to, or when this many instances of workers are trying to access a resource at once, you make the heuristic that means that the resource shouldn't be talked to anymore. So bulkheads, mental model, well, you can think of this kind of like a threat pool, right? You check out a connection and there's only a finite amount of connections that you can have at a time, but we do it on per server level. It's not global because then you have to have a data store, and sort of doing data stores within your resiliency primitives is really difficult. So we just do it per server. It ensures that you can really reason about how much is accessing something at once, and it fails faster than the circuit breaker when the timeout is still high. And they complement each other really well because the bulkhead still has the drawback of still reducing your capacity, and the circuit breaker fails really, really fast. So they complement each other really well. So you need both circuit breakers, bulkheads, and timeouts, at least we did in our case.
Simon, quick question about the circuit breaker and bulkhead patterns. Is that from the Release It book, or what would you recommend that people read up on that?
I would say the Release It book is really good on them. I'm going to talk about the projects where I've implemented all of this stuff so you don't have to as well, where I also have tried to explain them in depth. Release It is where we got all this stuff from.
Okay, great.
That's definitely the best resource. Because if you Google circuit breaker or bulkhead, a circuit breaker you're going to get like electronics, because it's a very common thing in like.
Oh, you can find software articles about it as well.
It's hard, and bulkheads is kind of like it's analogy to something on a ship. So it's just hard to Google about. If this is interesting to you and it seems relevant to what you're doing, then Release It is a fantastic book for this subject. Like you can consume it in 6 hours. It's a very quick read. So do you need this? Probably not. It took us a while before we got to the point where this is really, really important for us. I'm going to talk a little bit more about where I think you should start. And fortunately, you don't even have to implement it because we already did that. We created this library called Semian, which is a Ruby implementation that uses some fancy Linux APIs to do all this stuff across a host. If you have a lot of services and so on, your resiliency matrix looks like a mess, then this is definitely something to try and look into. But you should see this stuff in production before you start investing in it, because it is a significant investment. And if you just blindly include this library, which you can, and you don't understand the tunables, then this is probably going to be worse than before. So last thing I want to talk about is a little bit about process. So we've talked about how can you engineer your applications to respond really well to failures. But there's also the other side, which is how can your organization respond really well to failures. I don't know how many is familiar with the term anti-fragile. Some of you. So anti-fragile is this idea by a guy called Nassim Taleb, who's very smart and talks a lot about chaos and embracing chaos. And sort of his observation is that the opposite of fragile is not something that is robust or solid, right? Something that is fragile is something that breaks under pressure. Something that is robust or solid is something that is indifferent to pressure. What if you can create systems that under pressure become better? So I thought a lot about that, and you can't really do that unless you are doing crazy things where you can do sort of, I found some papers on this and started playing with it where you can do like genetic programming to at runtime patch dependencies and stuff like that. And that has so high complexity that it's just not worth doing. But it's an interesting thing to think about nonetheless. But your organization can definitely respond in a way where when you have one failure, you make sure that the next 10 failures don't happen, right? And that's sort of an anti-fragile response to a failure. You actually take the lesson from the failure and make sure that not just this failure doesn't happen again, but the 10 other related failures don't happen. A really good tool for this is something called root cause analysis. This comes from, it's very used in aerospace engineering when planes crash. And I don't know if you've ever watched the Mayday like air crash investigations. I particularly like to enjoy it on the planes when I'm and then if you can find one that is really relevant to your situation, like all the Atlantic ones or the Pacific ones, and if you're really cruel, you sort of like get an aisle seat and sort of but they're really good at this thing called root cause analysis. Every time a plane crashes, they spend a significant amount of time thinking about what exactly happened and how can we not just make sure that this doesn't happen again, but all these different other things, related things, don't happen either. So you try to go to the root and not just look at this symptom that caused it, but the completely underlying problem. And so you avoid all the next 10 failures as well. And often also, if you've ever read one of these root cause analyses for an airplane, which are ridiculously long, they don't just say like, oh, like this guy fucked up. It's usually this guy fucked up, then this happened, then this guy, then this other guy fucked up, and like it's always like 50 things, right? It's rarely just one thing that fails, it's these 50 things in a chain. The good news is that if you can intercept at any point in that chain, you're pretty well off. And an example of a really good root cause analysis that we had was that as a series of these Redis failures that I was talking about, we sat down and said that we're simply not good enough as a company, as an engineering organization, responding to these failures in our software. So we sat down a team of 5 to 7 engineers, of which I was among, to try and figure out how to get better at this as Shopify and sort of embed the knowledge within your organization. That's an example of really good root cause analysis because I can't count on all the fingers and toes I have how many incidents we've avoided since then. Another thing you can do is this thing called game days. This comes from the military does this a lot. Like astronauts will go into water and like navigate around a rocket to sort of get a feel for no gravity. Pilots will sit in simulators all day, and we can do this in software too, right? We can go and shut off servers or make things slow and so on, and see what happens. We can try to theorize a little bit about what happens to start with, but just going and turning on and off a server and seeing what happens is a really good exercise. And when you get to the point where you just turn off your master database and everything is fine and you lose a single checkout, you're at a pretty good stage. But until then, you're vulnerable, and it means you can wake up to these things, right? And it might sound scary to go and turn off nodes in your data center or ask someone to plug out a cable and see what happens, but it's going to happen at some point anyway, so why not do it yourself? And it's also really fun, and you can make it really fun because this is fun engineering. Google has this thing where they do these RPGs where you sort of sit down in a room and then you have a game master and he says, this fails, what do you do? This fails, what do you do? This is going to fail for 2 days, what do you do? And then you sort of get really, really good at this stuff and you make it fun. I think our game days are really fucking boring, but we're getting better. I have this idea of creating something called Monkey Script, which is where you sort of define all these failure scenarios and you can sort of give it your topology and then it does all kinds of crazy things. So I think that's a really, really fun exercise. We do this every single week, the different teams. So the team that I'm on then does it every month, where we just go on and like pretty much think about what is the most uncomfortable part of our stack and then we try to turn it off and see what happens. When you get really good at this is something that Netflix is really good at. They employ this simian army, which are all these scripts that just go and turn off shit in production. This gorilla here is their latest invention, and what he does is he goes and turns off an entire data center. So if an Amazon region is down, they do that. And that's really, really fun. And it means that if some teams within Netflix then disable it, and the resiliency team is like, yeah, okay. And then they wait, and then the CTO gets really mad at them for turning this off. And Netflix also has made it really fun with, you can imagine like you have the resiliency team on one side of the table, then the chaos team on the other side of the table, and they basically have this internal battle going on of like the chaos team trying to break things and like introduce latencies, and the other side of the table tries to keep it up, right? And this is really fun and something that you can do, you can make games out of it, right? And if you can create like some kind of internal visualization system where you can really easily turn things off, or you can ask someone from support to come in and like turn off some server and just make it really fun, right? And give people in the organization fun, or some kind of visibility into what happens. I often try to get some of my friends from support or sales to come in and try and like deploy Shopify. So just so that they know how easy it is, right? And the process should embrace it. And so this is a lot of information, and for most of you, a lot of this stuff is not really relevant right now. It's good to have in the back of your head because it knows, it gives you some idea of what is possible. But I think that what you should be doing is sort of think of this, I call it the resiliency maturity pyramid, where sort of as your organization and team grows and the amount of people relying on your product grows, you sort of traverse this pyramid, right? So we're at the point now where we need to be here. We need to be able to kill an entire data center and not really have it having any consequence. And this is one of the things that I'm working on right now. But most people just should be in this sort of orange region where you have toxic proxy tests for all your dependencies. You have you're starting to look at these resiliency patterns, or at least think about it. You might not use circuit breakers and bulkheads yet, but at least you have application-specific fallbacks. Maybe you have some meta-programming in place to make sure that everyone actually uses them. But sort of climb this thing as your scale and requirements